there a
All good?
clock or anything?
Okay.
So we know time?
Can you guys hear me okay? Yes. All right, good. So we're 2 minutes early. We'll get started because this is a topic which I think is a little bit more than 10 minutes. And I don't want to be the person standing between you guys and after a long, hard day and the beer. So we'll get this going. But this will be a worthwhile session for sure with all three of us.
Thanks for coming.
Thanks for coming, first of all. So today's session is warp speed Openvswitch, and how do you really boost the performance of an Openvswitch and really provide a turbocharged VNF that can do 100 gig per second for the next generation data centers. So I'm going to introduce my team as we go along in the presentation to just save on the time. But myself, I am Ash Palgat from Mellanox, and I'm Senior Director for Cloud Marketing. And just get right into the agenda here. As you know, the next generation data center needs are clear. You know, the NFV SDN data centers, 5G, IoT, these are all different applications and use cases. And they are needing a lot of higher performance from the infrastructure, mainly the NFVI. So we're talking about scaling up the services that need high bandwidth in terms of really millions of mobile flows for voice, video, data. We're talking about 100 billion plus virtual connections, which are all high bandwidth and high throughput requirements for all of those connections. We're talking about high performance infrastructure in terms of really high, lot of cores on the CPU to do really complex applications. We're talking about storage, that's all flash, to really be able to scale to do applications like augmented reality, virtual reality, machine learning. And all of that is really needing a lot of performance from the infrastructure. The network performance is obviously required in terms of really getting 25 gig or up to 100 gig on the NIC speeds. Low latency is a requirement. I was just in a talk today with AT&T saying that they really need edge computing to have 1 millisecond RTT as a requirement. Same thing I heard in the 5G networks when people are talking about edge computing or the requirements for latency. So all of these different use cases really need a lot of performance from the infrastructure. We, of course, need to save on the CapEx because it's not going to be a cheap infrastructure. It's going to be pretty expensive in terms of the capacity it has. So we need to use it wisely. And then on top of all of this, we need to make sure that there's multi-tenancy built into this infrastructure because you can support millions and millions of users and customers. Above all, as the telcos are telling us, we don't need any vendor lock-in. So this is really the requirements for the next generation data center. What do we have today is this survey from OpenStack, just a few months back, where we see that Openvswitch is the preferred switching infrastructure required for the OpenStack. Yet we know that there's a love and hate relationship between OpenStack and OVS because OVS is really slow in terms of the performance. It really doesn't scale in terms of the number of flows. It really burns a lot of CPU, and it drops packets, right? So on one side, you have a love relationship. On the other side, you have requirements that are really making you hate the OVS, and how do we solve that, right? So with that, I'm going to hand it off to Anita to kind of talk about how do we improve the performance of the VNFs, and she has some ideas on what do we do, and then we go from there.
Thanks. So looking very quickly, with OpenStack today, we have 3 options for your data path. You have Openvswitch, which is the default, and there is no tuning, and it gives you a whole bunch of kernel switching and capabilities. You have IGMP and live migration and tunneling and all the nice switching features that you want. Then you move to move on to the next level, and you have SRIOV, which gives you line rate throughput and with minimum CPU overhead, but no switching capabilities. All the switching is now moved to your top of rack switch. So if you need IGMP snooping, if you need tunneling, all that is on the top of rack. And then you move to OVS DPDK, which is, again, a kernel bypass option, but with DPDK, and gives you some switching capabilities, but it's a mid-range performance. So if you need to scale up and have like 100 gig performance, it's going to be very difficult to do. You're going to need a lot of cores and a lot of CPUs to achieve that. So let's look at what we can do as an alternative. This is OVS offload. OVS offload is a hybrid solution between SRIOV and OVS, giving you the switching functionality that everybody wants from OVS switch and also high performance all the way to 100 gig. And so given that 10 gig is now moving away to 25 gig on the server and 100 gig on the core. With OVS offload here, you have SRIOV directly connected to your VNFs and via VFs, and your PF assigned to your OVS bridge in the kernel data path. Your OVS eSwitch is now available in the NIC. And this solution is offering a TC Flower offload from the kernel, from the OVS bridge down to the NIC. But your OVS control is still untouched. It's sitting at the user level, your DB server and your vSwitch D, and you have your SDN controller and OpenStack controller sitting on top of that. For Red Hat, we're looking for a generic solution with multi-vendor support to enable these capabilities. And now you can actually do most rule matching and action offload, QoS marking, as well as tunneling offload, and basic firewalls support. If you're looking for more advanced features, that's in the works, work in progress, as well as fall back to the OVS host in case of failure. There are other options, VirtIO options, if you're looking for live migration use cases, and SRIOV doesn't meet that, then you have a VirtIO solution where you have an OVS DPDK bridge, which does DPDK switching down to the NIC, and you have a partial offload. Again, here, you're looking for QoS and security groups and contract offload, and this offload is happening via DPDK. And then you have another option, which is the embedded OVS, where OVS is completely in the NIC, including the control as well as the switch. And you have an SRIOV VF connection to the VM. Passing it back.
Thank you, Anita. So with that, I think Anita talked about a lot of different options for OVS offload. What we are proposing here is really the full OVS offload because it's best of both worlds. And what I mean by best of both worlds is you can keep your standard OVS control plane, but you can use SRIOV for your data plane acceleration, which gives you the maximum CPU, maximum throughput and minimum CPU utilization, which is literally 0. We have compared the numbers, and the OVS offload is actually better than OVS DPDK. Make no mistake, Mellanox has the best OVS DPDK performance in the industry of 133 million packets per second for VLANs. But we can do, for VXLAN itself, we can do 10x performance, PPS performance, with 0 additional CPU overhead for the technologies called as ASAP squared, which is our name for the full OVS offload. With the NIC speeds going from 100 gig to, from 40 gig to 100 gig, or from 10 gig to 25 gig, which is really good price performance advantage, you really want to make sure that the OVS is fully offloaded so that you don't really have a bottleneck in the infrastructure. I wouldn't go into all the details of the packet flow here, but essentially the packet flow is untouched except that we have the eSwitch at the bottom, which is basically taking the flows also from the OVS, the OVS switch D, which is allowing it to really function in a way that the user doesn't really know that an eSwitch exists at the bottom. So it's really completely transparent, and you do not have any overhead or any vendor-specific solution incorporated in that. If you look at what work has been done, like I said, there is one of the requirements in the next generation data centers is you don't want any vendor lock-ins. All of the work here that's been done is non-vendor specific. That's why I want to just make sure it's vendor agnostic. It's all done in the community, and there are multiple communities that we have worked with, all of us, and there are other NIC vendors as well who have contributed. And these are the OpenStack community, where we added new port type bindings. There's the DPDK community, where we enhanced the RTE flow API. There is OVS user space, where we have added the flow offload through the traffic control API. And we also improved the TC Flower API itself in the Linux kernel community. So all of this is work. At the end, you'll see a reference slide, which we don't have much time to talk about. But all the work and the patches and the white papers that we've written in the community is all available for you guys to see later. So with that, I'm going to give most of the time to Mark to finish up this presentation to talk about the main thing in this presentation, which is the numbers. So let's go to that.
OK, thanks. So as you've seen, there's quite a few different moving pieces here in order to put together a complete and working OVS offload. So there's upstream work that's been happening not only in OVS, but also with the Linux community, the OpenStack community, DPDK. Anyway, let's try to put some of it together and actually see what kind of numbers we can actually achieve. So this is a very typical cloud scenario, cloud networking scenario, where you have a pair of virtual machines, a pair of hypervisors running virtual machines, connecting through a VXLAN tunnel. And what we'll do here is run two different kinds of tests. First, we'll do iPerf, where we're using TCP-type connections with relatively large I/O requests, 32 to 64 kilobyte type I/O requests. and then look at how the performance plays out there. And then the next test that we'll do is for small packets doing UDP type interactions. And for that, we'll use a DPDK-based packet generator, T-Rex, and we'll do a forwarding application called TestPMD. People that work in this field probably know these applications, but basically, we'll look at the round trip throughput in that scenario as well. And then we'll consider two different data paths, right? So we've talked here now about how this OVS offloading will work. So it's basically ASAP Direct is the name that Mellanox has adopted. But what that represents is basically SRIOV down to a NIC. And the NIC actually has the flow information and allows you to do the switching on the NIC as opposed to having to go out, for instance, to an external router or some other VTEP device. And then we'll compare that with a more traditional OVS where the kernel module is actually doing the packet processing for the tunnels. And we're using VirtIO for the VM interface. So with that, I guess I have to push a button here. Yeah. And the specs for our setup here, I didn't mention it, but we're using Haswell processors. We're running RHEL 7.4. We have a 100 gig interconnect. We actually have two of them. And then we're using 1,500 byte MTUs inside the VMs. And we have a 9,000 byte MTU on the underlay. OK. So this is the iPerf case. And what we're looking at here is red and green. So red is the iPerf results using a VirtIO interface and kernel module OVS. And we're comparing that with the OVS offload that's delivered by ASAP Direct, which again is SRIOV plus switching happening on the NIC itself or inside the NIC. So the chart here shows you throughput on the x-axis, going all the way up to almost 100 gigabits per second. And that's the actual data throughput. So it's not including the header throughput. So that's a little bit of overhead that would naturally prevent you from being able to get all the way to 100 gigabits per second in that measure. And then we're showing what the CPU utilization is. And so what we're charting here in terms of CPU utilization is OVS plus iPerf. And it's important to understand that so that you can understand why we're seeing CPU usage, even though we're doing OVS offloading in this case. What you're really seeing in the green here is the iPerf utilization. So what you see also is the red stops at 30 gigabits per second. Essentially, you can't, at least with the setup we had, we couldn't get beyond 30 gigabits per second of throughput. I mean, things just begin to break down. And the other thing you see is that the red bars are roughly twice as high as the green bars where we have them. So that means that it takes twice as much work to do the same throughput if you're using VirtIO as opposed to ASAP Direct or SRIOV. So there's a tremendous win. And actually, if you can convert that into effective cores, that represents about 7 cores in my system, which had 32 cores altogether. And in fact, we were only using one VM with 12 vCPUs. So in a sense, 7 vCPUs were saved out of the 12 just by moving to the ASAP Direct and pushing the networking down to the NIC itself. So those are very interesting results. And so again, you see there's a big CPU savings and much higher throughput for a case that is probably not completely unrepresentative of computing that would go on in a cloud environment. I'll also point out that in a background of about 20 gigabits per second throughput, I did take a look at the ping latencies. Ping's not an ideal way to measure latency, but still you can compare the difference in latencies that way between the two different data paths. And you can see there's a substantial improvement in or reduction in latency for the packets when you're using ASAP Direct. And that's very important, when you get into these environments where, for instance, you have a 1 millisecond deadline to turn packets around, for instance, in a 5G network. So that's really very important. this is the second case. Here we're using DPDK-based packet generation and also DPDK-based packet forwarding, one on each system. So it's T-Rex. Again, some of you in the audience are familiar with that, and then test PMD on the other side. So what we really took a look at is like how much CPU usage do we have to give to the forwarding application, which is essentially a representative VNF. Test PMD is acting as a representative VNF in this case, in order to process as many packets as we could possibly throw at the system. So these are very, very small packets. They're probably on the order of 64 bytes. I didn't check exactly, but they're really small. And what you see here is, again, CPU utilization is a function of throughput, but now throughput's measured in packets per second, okay? And essentially, you see no difference in that green bars. No matter what the throughput was, everything was frozen because we're basically using a DPDK app, which has a polling mode driver in it, which is just locking down 6 cores. And it turned out that 6 cores is the number of cores I had to have in order to obtain the maximum throughput that we could. And the maximum throughput that we achieved was roughly 56 million packets per second, which is somewhere close to warp speed in my book. I'm not quite sure what it is really, but that's a very large number, and it shows great promise in terms of what we can do in the future. Obviously, there are a lot more tests we'd like to run, and we'd like to kind of build this all out and have a much more comprehensive database that explains what the real benefits are and how this behaves. There are things like increasing the number of flows, looking at latency more carefully. There's a lot of other tests that could be done, but this is sort of a down payment that shows the real benefit of pushing the OVS processing down to the NIC. So I think it's a very good result, and I hope we can come back and give a little bit more lengthy presentation at the next summit.
All right.
So with that, I think we provided a bunch of references for anyone who's interested in various aspects of what we do, and we're done.
Okay, thank you. So just to summarize, OVS offload, we get 3 key benefits. One is you get the line rate throughput for the large packets. You get the best packets per second with the smaller packets. You get no additional CPU overhead, beyond what you need to do in terms of really using what's running on your system. And then it's all software programmable because it's all community-driven and it's all programmable because it's all software-defined. That's all we want to convey today. Thank you so much for your time.